All right. Good morning, class, or good afternoon, whatever time it is you happen to be watching this video. So welcome to Math 2164, Section 081. This is the Summer 2 course. Today is the first day of class, July 5th. So basically, as you may have seen from the announcements and from the syllabus, it's been sent out to the class. This is an online course. What that means is that we're not going to have any in-person lecture. There's also not going to be any Zoom lecture. Partly that's because that since this is an online class, it's possible, and in fact, I happen to know several of you have various internships and such. And so due to that, you're taking online class because you're actually not able to meet for class, and that's fine. So if you're a student who's out of town, who's not in Charlotte, that's fine. I'm not expecting you to be in Charlotte. And if you are in Charlotte, that's also okay. If you'd like to come by and talk to me or something on campus, that's fine. You can email me. We can set up a meeting. We can do that kind of thing. But otherwise, this is a online course, so all of the lecture material is going to be covered via these videos. I will record them daily. Some of them I'll try to record ahead of time, and then they will be posted onto my YouTube channel, and then they will be put in that folder, that playlist for this class. So that will be connected to Canvas, and of course, I'll send out that announcement, so you'll see all that information. Right, so that's how it's going to operate. I will be offering, probably beginning next week, office hours. Now, those office hours will be held over Zoom, so I'll send out a Zoom join link that will be available. I'm not 100% on what time it's going to be offered yet. However, I do believe it's going to be like a Tuesday, Thursday thing. But again, since this is an online class and I realize many of you have internships or full-time jobs during the day, then because of that, we will likely have the Zoom meetings occur in the evening. That way, if you're working during the day, you can still attend the meeting in the evening. Of course, it's not going to be super late. I mean, I'm thinking like maybe 6 o'clock. That'd be available for like an hour on Tuesdays and Thursdays. But I'll send out an announcement with more of this information later. So great, that's something on the way. We'll start the office hours next week. I did want to take a moment to talk a little bit about Canvas briefly. So the participation questions, this is kind of like the form of attendance that we're using for this class. The participation questions are just going to be simple 1 minute, 2 minute questions at most. They're not designed to take a lot of time, but they're going to be questions that are relating to the lecture material for that day. So we'll cover the lecture material. In fact, during these videos, I'm going to talk about the participation question and answer them during the video. So if you're watching these videos, those participation questions are designed to be a free 100 if you're following along with the material. So by all means, please do take advantage of that. I want you to take that advantage. I want you to get hundreds on those. They're not supposed to be tricky. It's just a way of keeping track of, who's keeping up with the material and who's not. So the rest of the homework will be turned in via handwritten paper. So you'll have to write out the homework on paper, and then you can take pictures. I suggest using an app like Cam Scanner. It's a free app. You don't have to pay anything, and you don't even have to make an account or anything. And the reason I like Cam Scanner is that it allows you to take pictures of your handwritten work, and then it's going to automatically convert it into a PDF, and then you can email it to yourself, whatever you want to do with it. And then you can have that electronic version of your homework, and that is what will be uploaded and submitted to Canvas. Now, homeworks are going to be due, let's see, let me look at the schedule. So if you go on Canvas, look in the resources on the home page, and then schedule. The first homework will be due July 11th. So that will be this coming Tuesday by midnight. I'll post more information about that on Canvas as well, so you'll have all that. So the homework will be submitted on paper, but you'll take pictures, upload as a PDF, so on and so forth. But whatever medium you're using, that's fine. So long as I'm able to read your work, I'll be able to grade it, and that's all I really care about. With that being said, though, I have run into issues where any individuals who are possibly using iPhones or other Apple products to take their pictures, Apple saves and creates images as HEIC files. They're some kind of like high definition something or another. Not 100% what that stands for. But the point I'm getting at is that HEIC files can only be viewed on Apple products. So if you upload it as an HEIC file and I'm on my computer on campus, the computer that's provided to me by the university is not an Apple. So I cannot open or view an HEIC file. So if you submit your homework as just a picture with your iPhone or other Apple product, I'm not going to be able to view it. I'm not going to be able to grade it, and I'm going to give it a 0. So that's why I strongly suggest, use something like Cam Scanner that will turn it into a PDF file, and then I can read it, and it doesn't matter what kind of phone you're using, I'll be able to view it and grade it, and then you won't get a 0. So please, if you are using an iPhone or something to take your pictures, that's fine. Just make sure you convert it to a PDF, because if you leave it as an HEIC, I cannot view it and you will get a 0. So watch out for that. Right, so that's homework. I'll post more about that on Canvas later today. Participation questions, daily things. So we'll have one today. Participation day 1 will be covered today. So we'll talk about that in a moment. Otherwise, each video is going to be covering the lecture sections that are mentioned in the schedule. So today we are covering sections 1.1 and 1.2 of our textbook. So I'll do that here on the board here in a moment. But this is also following the very same lecture notes I have posted on Canvas. Those lecture notes are my handwritten notes that I've used in teaching this class previously. So they're the exact same notes that I'll be using here on the board. The only difference is that I'll be talking through the explanation here in this video versus if you're just looking at the notes, while it has some handwritten explanation, it's not going to have everything written I'm going to say here during the video. So, take that as you will. If you're a student who doesn't really need the video and lecture notes are enough for you, or the textbook is enough for you, that's fine. Go for it. But I do recommend these videos, especially since I will be covering the participation question in these videos, and they're not covered in the lecture notes. So do with that information as you will. Okay, great. With that being said, let's go ahead and start today's lecture. So we are looking at section 1.1 and 1.2. Of course, as you might guess, and fair warning, as I'm writing on the board, my face is going to come in and out of the video. Just the way it is. I have this whiteboard here I'm writing on, but we're going to make the most of it. Okay, so what are we talking about? Well, this class, as you might guess from the name, is linear algebra. What does linear algebra mean? Well, if you may recall from your algebra classes in high school, we're going to be talking about linear equations. What's a linear equation? It's an equation that when you graph it, it is a line. Now, if you're familiar with in a two-dimensional space, so when you have an x-axis and a y-axis, you can have a line. And this line has the form y equals mx plus b. This is a linear equation. Now, as we progress in this class, of course, this linear equation is an equation described in a two-dimensional space. You have an x-axis and a y-axis. As we continue in this class, we're certainly not restricted to 2 dimensions. We can have linear equations in 3 dimensions, 4 dimensions, 5 dimensions, 6 dimensions. We can have a linear equation in whatever dimension you like. The only dimension case we're not going to talk about is the infinite dimensional case. And that's only because when you get to the infinite dimensional case, things kind of get a little more crazy. It gets beyond the scope of this class, so we're not going to worry about that. So everything we do in this class is going to be within a finite dimension. Right. Okay. So what then is a formal definition for a linear equation? Because a linear equation is not necessarily always y equals mx plus b. Because this is a two-dimensional equation, it's not the only type of linear equation we can have. We can have linear equations in higher dimensions. So what does that look like? Well, here's where we have our first definition. For the sake of this class, when I'm writing out definitions, I'm going to write DEF to indicate I'm abbreviating here. Let's see. Let me make sure I didn't write off of the screen. Okay, good. It's on the screen. Perfect. Okay. So I'm going to write DEF for definition. So what is a linear equation? I'm going to abbreviate here. A linear equation is a first degree polynomial. What is a polynomial? You may recall from a college algebra class or whatever math classes you had in high school. A polynomial is something like a quadratic where you have like x squared plus x plus x plus c, so on and so forth. A polynomial is just referring to you have some number of x's with some powers being added together. But we're specifically looking at first degree polynomial. What does that mean? That means we're talking about polynomials where the highest power is 1. There's no x squareds, right? Why do we not want an x squared? Well, if you graph y equals x squared, it's a parabola. That's no longer a straight line. That's not what we're talking about. We're only looking at linear equations. So these are first degree polynomials. And if there are n variables, so in the example here with the two-dimensional case, y equals mx plus b, there are 2 variables, y and x. The number of variables are directly going to relate to what dimension of space we're working in. So if we have n variables, that means we are in a n-dimensional space. So if there are n variables, then our equation is going to look like this, where we have a sub 1, x sub 1, plus dot, dot, dot. I'm doing this dot, dot, dot because there's also an a2, x2, a3, x3, a4, x4, so on and so forth, until we get all the way up to an xn equals b, where a1, a2, dot, 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 and b are constants, right? In other words, the only variables in this equation is the x1, x2, x3, x4, x5, so on and so forth, all the way up to xn. These are the only variables in this equation. And I also want to introduce this notation where I'm using these subscripts. Now this x1, this isn't saying it's x times 1. This is saying x subscript 1. In other words, this is just a way to differentiate which variables am I talking about. X sub 1 and x sub n are 2 different variables. So we're going to use this subscript to indicate when we're talking about different variables. But the point here is that we have n variables. Each one could have some constant being multiplied on it. Just like in y equals mx plus b, we have a constant times the x. But then we could also have some other constant on the end, which does not have any variable attached, just like we have this b here in y equals mx plus b. So every linear equation is going to take this kind of format. So you want to get used to this kind of idea, get used to this notation, because we're going to see it forever and ever in this class. So fair warning. So what are linear equations? It's first degree polynomial, right? So think of any equation you like, which is a first degree polynomial. We can have 2x1 minus 3 equals x2, and you can write whatever you want so long as you're not breaking the rules. You can only have first degrees, which means you can't have a variable times a variable at all. You can have a variable to a power. We can only multiply variables by constants, and we can add them together. We can't multiply variables. So, for example, this is linear versus if I write 4x1 minus 5x2, which so far hasn't broken any rules. This is a first degree polynomial so far. But then if I say equals x1, x2, well, now I have a variable times a variable. That's no longer linear. A linear equation is not going to multiply the variables. So we're never going to have this happen in the class. This is not linear. Of course, if during these lecture videos you end up having questions, by all means, email me. We can talk about it. Or write down your questions, and we can talk about them during the office hours. Okay, great. So this is our notion of what it means to have a linear equation. Now, in this class, we're oftentimes going to have more than one linear equation at play at the same time. So what is that? How does that work together? This is when we have a system of linear equations. So a system of linear equations is a collection of, as you might guess, linear equations. I'm going to abbreviate here, EQ. Linear equations, but here's the key, using the same variables. In other words, they are linear equations that exist in the same space. They're either all equations that exist in a two-dimensional space, or they're all equations that exist in a three-dimensional space. We're never going to mix equations from different dimensions, because if you have equations in different spaces, different dimensions, their solution set is going to be different. The solutions you're going to get for those equations where they overlap, they're going to be different, or they might not even exist at all. So what that means is, and I'll write this up here, leave the definition below. Now, of course, I expect what we're covering today you've probably seen or heard before. But as we continue, this is a video, so by all means, you can pause it if you feel like you need to write something down before I erase it. But that shouldn't be so much a concern with today's video. Okay. So a system of linear equations, we want a collection or a set of equations using the same variables. So for example, if we're thinking about the two-dimensional case, and for today, just to keep things a little simple, I might leave things in the two-dimensional case just so that we can get used to what we're talking about here. But we could have the equation y equals 2x plus 3 and y equals 2x minus 4. Now, these are linear equations in a two-dimensional space, so we can graph them. And I mean, even if these are equations that are three-dimensional, you can still graph those if you have various programs like Mathematica or something else, Maple. You can still graph them. Once we get to 4 dimensions or above, it's going to be more tricky to actually graph these. So you're going to have to more visualize them in your mind. Right. So 2x plus 3, okay, that's a line with an intercept at 3, a slope of 2. And the second equation has an intercept at -4 and also a slope of 2. Now, you may recall from your past algebra classes, these lines have the same slope, so they are parallel. Well, if they are parallel, that means they are never going to intersect. So what does that tell us? Well, any system of linear equations, we're concerned with trying to find the solution set. Let's let me not go too far off the screen. Okay. Right. What is a solution set? The solution set is going to be the set of all possible solutions to a system of linear equations. What does it mean to be a solution? We're looking for pairs of the variables. In other words, we're looking for what variables are going to be true for all of the equations at the same time. So what, or rather, the solution set is the set of variables which satisfy the equations in the system. When I say system, I'm referring to the system of linear equations. So we're looking for what are the solutions. In this case, there is no x and y which satisfy both equations at the same time. This is an example where there is no solution. In other words, the solution set is the empty set. What is the empty set? Well, if you've taken like discrete math or other classes like that, you've probably seen before. This is just a set which literally by its name has nothing in it. It's empty. There is no solution which satisfies both these equations at the same time. So the solution set is an empty set. There is no pair of variables that's going to satisfy these equations. So this is a possible outcome we can run into in this class. If I change this a little bit, I can have y equals 2x plus 3 and y equals 3. Now I want to highlight here, our definition for a system of linear equations said it had to be a collection of linear equations using the same variables. But here, the second equation, it doesn't seem to be using x. So how can this be a system of linear equations? Well, as in the case for a two-dimensional space, it could be that you have some equation and it's just x is not used. X is not relevant. And so even here, while x is not specifically written in the second equation, you can think of this as plus 0x. And so in this way, both equations are still using the same equations. It just so happens the second equation has x multiplied by 0. This is a concept we're going to see pop up over and over and over again. So you want to get used to this idea that if you have missing variables, well, they're really still there. It's just that they're being multiplied by 0 is another way of thinking of it. So in that way, this is still a system of linear equations. It's still a collection of linear equations using the same variables. It just so happens one of the variables got multiplied by 0. Okay, what does this mean? Well, when you graph it, we still have this y equals 2x plus 3. And now we have the line y equals 3. And lo and behold, we have a solution. Now, of course, we only have one intersection with these two lines. So there's only one point, one pair of variables, which satisfies the system of equations. This is an example where we have one and only one solution. And then the third case that can happen in this class is, well, what if we have a line like 2x plus 3, and then it turns out we have a duplicate of the line, 2y equals 4x plus 6. You can see here, what did I do? Well, I really just took this equation and multiplied everything by 2. So when you graph this, it's just going to be one line on top of the other line. So it'll look something like this. And here we have infinitely many sets of points, or sorry, we have infinitely many points in our set which satisfy it. This point works, whatever that is. This point works, 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 so on. We have infinitely many points on this line, right? Because a line, of course, is infinite, right? So we have infinitely many points, we have infinitely many solutions. So this is going to be the case that we run into forever and always in this class. Whenever you're trying to solve any kind of system of linear equations, which really is all this class boils down to, we have three cases that can occur. Either you're going to have no solution, you're going to have only one solution, or you're going to have infinitely many solutions, and there's no in between. It's impossible to have exactly two solutions with linear equations. Why? Well, if you had two solutions, that would mean somehow this line bent around and intersected again. But a line can't bend like that, right? A line can only go in a straight path. It's not going to be able to bend and intersect a second time or a third time. And so because of that, straight lines can only intersect at one point, or they can be directly on top of each other and share every point in common. So we have this distinction of you either have finite number of solutions, which means you only have one, or you have infinitely many, and there's no in between here. Okay, good. We also, yeah, let me go ahead and introduce this vocabulary. So we can see here that with a system of equations, sometimes we have a solution, sometimes we don't. In particular, if a system has a solution, then it is called consistent. Consistent just means here that a solution exists. There is some point somewhere that is going to be able to satisfy all of the equations in our system at the same time. So it is consistent. Otherwise, if a solution does not exist, so this is the case where a solution does not exist, the system is inconsistent. So this is the scenario, like over here with this first example, there was no overlap. There are no pairs of variables, which are going to satisfy both equations at the same time. And so there is no solution here. This is then called an inconsistent system. Whether you have one solution or infinitely many, they're both called consistent because all consistent cares is whether a solution exists at all. Doesn't care how many solutions. The other thing that you want to be wary of here is that the terms consistent and inconsistent only apply to equations where we have these equal signs going on. When we're talking about solutions, that means we're talking about things that satisfy some set of equations with equal signs. If you do not have equations that correspond with equal signs, you cannot use the words consistent or inconsistent. These are terms which only apply in this specific setting when we're dealing with a system of linear equations with these equal signs. The reason I'm harping on that is going to become more clear in a moment when we start looking at matrices, but we'll get there. Right, okay. I'm going to go ahead and erase this then. Now the trickiness comes into play, all right, two-dimensional case, that's fine. We know how to do that. We know how to, solve for one variable, plug into the other equation, solve for the other variable, so on and so forth, just like you did in high school algebra. Nothing new there. The trickiness is that when you have 3, 4, 5, what if you have 20 variables? What are you supposed to do then? Are you supposed to solve for 20 different variables, plug them into each other, painstakingly try to solve it out and then plug it into another equation, so on and so forth? Do that 20 times? No, that's not what we're going to do. That is a very bad way to solve these kind of problems. There are much more efficient ways to solving them. And really, that's what this class is going to boil down to. We'll talk about other properties that appear with these kind of problems, but that's going to be later down the road. Okay, so what is a matrix? Well, first, let's start with the system of equations. Here I have x1 minus 2x2. And again, these are subscripts just referring to, I'm talking about two different variables, x1, x2, plus x3. So now this is a linear equation that exists in three-dimensional space. And then I can have 2x2 minus 8x3 equals 8. And then I can have 5x1. And I'm intentionally leaving space here where I'm jumping over and writing minus 5x3 equals 10. Now, this is going to be a little bit different from the example that's in the lecture notes. This is following the example that's in the textbook, so you can look at the textbook and see step by step what I'm doing here. So this third equation is quite literally just 5x1 minus 5x3 equals 10. But I'm leaving this gap to indicate there's no x2 here, right? There's no x2 in the third equation. So because there's no x2, and we know a system of linear equations has to have the same variables, it really just means there's a 0 x2 here, right? Just as, and just for practice, I'm going to write in 0 x2. As we continue in the class, I'm not going to do this every time. I'm just doing this today so you can get used to visualizing what's happening here. But again, this is not something I'm going to do the entire class time. So we have these missing variables. That's okay. What we're really checking for is that we're assuming here these equations are all using the same one. So they're all using x1, x2, x3. So we can turn this into a matrix. In fact, we can turn it into what is called a coefficient matrix. What is a coefficient matrix? Well, it's just a matrix where we're going to take the coefficients attached to each variable and just write those coefficients. So each row of the matrix is going to correspond with an equation. Each column then is going to correspond with some variable. So the first row, this is equation 1. The second row is equation 2. The third row is equation 3. First column is associated with x1. Second column with x2. Third column is x3. And there isn't another column because this is the coefficient matrix. I'm only looking at the constants, which are coefficients to my variables. So my matrix here is going to be 1, -2, 1, 0, 2, -8. And this is why it's super key to be imagining in your head that, like, oh, if you're missing a variable for some equation, you need to put a 0 in that position. So it's going to fill in that space when we're writing out our corresponding matrix. 5, 0, -5. So this is the coefficient matrix. Note, this matrix does not care about the equals here. It does not care about equals 0, equals 8, equals 10. This matrix only contains the coefficients. So if we go back to the terms of consistent, inconsistent, as we were talking about just a moment ago, those vocabulary terms do not apply to this kind of matrix, right? This matrix you cannot say is consistent. This matrix you cannot say is inconsistent, right? So I want to really drive home that point, because every semester I have students try to say this matrix is consistent or inconsistent, but you can't do that. There's no equals here. The equals column here is not included. There is no equals column. We're only talking about these three variables, no equals column. These are not equations with equals. So this matrix, you cannot say consistent, you cannot say inconsistent. However, if we instead talk about the augmented matrix, what is the augmented matrix? Well, it's the exact same thing we just did, except now we also have an equals column. So the augmented matrix is going to copy all of these constants. And so really the only difference between the augmented and coefficient matrix is that one has the equals column, one does not. And in fact, even for further clarity, you might see in the textbook notation, sometimes to differentiate the equals column from the other columns, they're going to put like a little dashed line here. Sometimes I'll do that in class. Sometimes I won't. It just depends on the problem, whether or not that's helpful or not. But this is another way you can write this if it helps you differentiate the difference here. But now for an augmented matrix, since we have an equals column, now you could say, okay, is this matrix consistent or inconsistent? But if it's not an augmented matrix, you cannot use those vocabulary terms. They do not apply. So watch out for that. Okay. Furthermore, when we're talking about this augmented matrix, we would call this a 3x4 matrix. When we're talking about the sizes of your matrix, or in other words, the dimension of each side of your matrix, it's always going to be rows first, then columns. Now I'm going to abbreviate columns COLS. That's just out of laziness, so I don't have to write out the entire word. I'm also doing that just because we're going to talk about columns over and over and over and over and over again throughout the rest of this class. Columns are super important when we're talking about matrices. Right. So this is a 3x4. Oftentimes what I tell students, in order to try to keep it straight in your head, how do you know that it's a 3-row then 4-column? I personally think of it in my own head, just to keep it straight, as imagine a matrix as being some building. If I'm trying to climb on top of the building, I first have to go up the side with a ladder or something, and then I can go across the top of the building, right? So it has to be rows first, then columns. You have to climb up the building first before you can go across it. Maybe it sounds dumb, I know. That's just the way that I keep track of it. Maybe that'll help you. Okay. Now, I want to talk about how would we actually solve this thing now that we have 3 variables. So I'm going to erase some of this here. I'm going to keep the augmented matrix because the augmented matrix is actually what we're trying to solve here. The coefficient matrix will be more important later in the class for other things. Not going to be super important for today. Okay, so if I wanted to solve this, one methodology that you might remember from college algebra or high school algebra would be you might try to add these equations together so that they can cancel out. All right, how might you do that? Well, I have x1 here in the first equation, but then I have 5x1 here. Well, that's not super helpful. I'd like to get rid of this x1, so I only have one x1. So how would I do that? Well, I could take equation 1. I'm going to write this as 1, 2 with a circle, 3. I could take -5 times equation 1 and add it to equation 3. Okay, what would be the point in doing that? Well, when I do this, we're going to have -5x1 plus 10x2 minus 5x3 equals 0. I'm also multiplying with the equals column. It just turns out -5 times 0 is still 0. When I add it to equation 3, well, I have no x2 here, so I can write 0x2 if I like. Minus 5x3 equals 10. So when I add, I'm going to have, oops, that should be an x1. I'm going to have 0x1, 10x2 minus 10x3 equals 10. So what I've done here is that I'm modifying the third equation because I want to get rid of the x1 here, or rather I want to reduce the number of variables so I can possibly get a variable by itself. If I have a variable by itself, then I can solve for what that single variable is. This was, I forget the name for it actually off the top of my head. But this is a strategy you would have learned in a high school algebra class or a college algebra class. But what I've done here is actually what is called a row reduction step. I am modifying an equation. In other words, I'm modifying a row of the matrix by adding a multiple of another row to it. In other words, I want to change row 3, which I'll call little r subscript 3. I'm changing R3 by, well, I want to take R3 and add a -5 times row 1. That's what I've done here. So my new matrix is going to be 1, -2, 1, 0, 0, 2, -8, 8, 5, 0. Oops, sorry. Our third row changed, right? So now we have 0, 10, -10, 10. Now what's kind of key here is that now this is the only place where I have a non-zero entry for column 1. This kind of approach is going to be key as we continue to try to solve this. I want to do the same thing for x2 and x3. And let's see. For the sake of time, I'm going to skip over some of the steps here. If you go in the textbook and look in section 1.1, you can see step by step what's happening here. But the punchline that I want to jump to, the punchline, let me scroll to it in the textbook. So if you continue doing this, what is called row reduction here, where you're modifying a row by adding a multiple of a row to the row in order to try to cancel some variable, which is the exact same thing you would have done in high school algebra by multiplying an entire equation, adding it to another equation to cancel out variables, so on and so forth. You can imagine here, one thing you could do is, well, now I could take equation 2 and I can multiply it by a -5 to get rid of the x2 in the third equation. Why would I do that? Well, if I do that in this next step, then I'm only going to have x3 for my third equation. My third equation will only have one variable, and then I can solve for x3. So what's this next row reduction? I want to modify the third equation, in other words, row 3. I want to take row 3 and I want to add -5 times row 2. So what is that going to do? Well, row 1 doesn't change. Row 2 is not changing. I'm only changing the third equation because I'm trying to get rid of all the variables there. 2 times -5 is -10. So when I add, I'll get a 0 here. -8 times -5 is a +40. Minus 10 is 30 here. -5 times 8 is a -40. Plus 10 is -30. Right? This is what the third equation would turn out to be if I wrote it out like we did up here. As we progress in the class, you're going to start to do this very fast, just like I did here, without writing the equations. But these are the equations in the background that are happening as we do these row reduction steps. But what's the point here? I've got x3 isolated here in the third row. And what does this say? As an equation, this says 30x3 equals -30. In other words, we now know x3 has to be -1. So now we're saying, okay, there might be a solution to these three equations, but whatever that solution is, x3 has to be -1. What about x1 and x2? Well, we'd still have to solve for them. We could use the second equation here, where we got this x2 kind of isolated. We could use that to solve for x2. And now that we know x3 is -1, we could plug that into the second equation, solve for x2. For the sake of time, I'm not going to write all of that out, but these steps are shown step by step in the textbook for 1.1. The punchline here is that x2 is 0 and x1 is 1. So this is a system which has a solution. This is then a system which is consistent. So I could ask you a question on homework or on a test. Is this matrix consistent or not? You could say, yes, the matrix is consistent. Is consistent. Why? A solution exists. Now you can do that with an augmented matrix. Again, I want to highlight, if I give you just a coefficient matrix and it is not an augmented matrix, you cannot say that matrix is consistent. That word does not apply there. So please don't do it. You will lose points for that. Okay, good. I'll leave this here for a moment before I erase it. That was the main point I wanted to highlight in 1.1. Oh, I do want to give an example of an inconsistent system. So this was our example of something which is consistent. In other words, when you row reduce, this is what's meaning by you're using these row operations. Row reduction means you use row operations to reduce your matrix so that you get all these zeros to appear in it. So when we row reduce the matrix, a solution appears, right? How can we tell if a matrix is inconsistent? All right, well, we said earlier that the equation, let me go back to it. Yeah, we said the equation y equals 2x plus 3, y equals 2x minus 4. We said this is inconsistent. Now we can rewrite it in the same format we've been using, where all the variables are on the same side. Right? Y and x are on the same side, just like x1, x2, x3 were on the same side in that past example. This, as an augmented matrix, is 1, -2, 3, 1, -2, -4. Right? So this is an augmented matrix. If I want to solve this problem, we know Okay, I want to isolate my x1 here, which means I want to get rid of the x1 in the second row. So I want to modify row 2 by taking row 2, and I want to subtract row 1 from it. Right? So notice when I'm doing these row operations, I'm not putting any scalar, I'm not putting any coefficient on the row I want to modify. If I want to modify row 2, I'm not multiplying row 2 by anything. Instead, I'm multiplying the row I'm going to use to cancel something. I'm multiplying the row I'm using to cancel something by some coefficient that's going to make the cancellation happen. But since I'm modifying row 2, I'm not multiplying row 2 by anything. This is going to be a key point later in the class. You want to hold on to this notion of row reduction. Okay, so what happens? Well, I'm taking row 2, subtracting row 1 from it, so I'm going to have 0, 0, -7. Well, what happened here? Remember, rows represent equations, right? So this second row as an equation says, so row 2 here says 0x1 plus 0x2 equals -7. In other words, 0 equals -7. But that's nonsense, right? We know that's nonsense. We know 0 does not equal -7. So for that reason, we can see that, aha, from this matrix, we can tell that this system is inconsistent. No solution exists. Why is it inconsistent? Well, if we were to believe a solution exists, that would mean we would have to believe 0 equals -7, which is nonsense, right? So this matrix is inconsistent. This augmented matrix is inconsistent. But we already know from when we graphed these equations that no solution was going to exist. But this is how we can see it in matrix form. If you have a row with some equation which says that 0 equals something which is not 0, right? This is where the inconsistency is going to pop up, which is going to relate to today's participation question. In fact, we can go ahead and look at that real quick. I'm going to go ahead and share my screen for that, actually. Let's see. Share screen. Entire screen is fine. Share. It cut off the microphone. Okay. Share entire screen. Here we go. Okay. So I'm sharing my screen now. This is my Zoom, so it's probably getting like some kind of weird double effect. Here's participation day 1. So if you go in Canvas, click on participation day 1. In fact, I'll do this in student views. This is what it's going to look like from your perspective. You're going to see some questions. It's going to say, is the below augmented matrix consistent or inconsistent? Does a solution exist? Now, lucky for us, this augmented matrix is it's already been reduced some. So we can look at, what's happening in this final row. Well, in fact, this final row, just like the example we just did, says 0x1 plus 0x2 plus 0x3 equals 10. In other words, row 3 says 0 equals 10, which is nonsense, right? So this augmented matrix, because we have a 10 all by itself with all zeros to the left of it in the equals column, this is going to tell us this system is inconsistent. Now, if this 10 here were instead a 0, that would be fine, right? It's okay to have a row of all zeros. Having a row of all zeros is okay because what does that say? If 10 was 0, row 3 would instead say 0 equals 10, which, yeah, that's true. That's correct. But because we have a non-zero in the very last column with all zeros to the left of it, it tells us this augmented matrix is inconsistent, therefore a solution does not exist. So how would you get credit for today? You go up to click Start Assignment. You're going to type in, is the below augmented matrix consistent or inconsistent? The answer is inconsistent. Then it asks, does a solution exist? So because it's inconsistent, therefore a solution does not exist. And that's all you have to type. For these participation questions, I'm not looking for you to type out some long, lengthy explanation for why your answer is correct. I'm just looking to see if you have the correct answer, because I'm going to give you the correct answer during these lecture videos. So I'm just looking to see, okay, do you have the correct answer? That's fine. That's all I'm looking for. This is all you have to type for today. Inconsistent, therefore solution does not exist, so on and so forth. And okay, great. You then are going to click Submit Assignment. And that's it. It's done. That's all you have to do for the participation questions. I might not always type it in word for word and show you like this, but I will, like, if it's a problem where we have to solve it or something, then I will do the work on the board and then circle the answer for what I would expect you to type in the participation question. Okay, that's today's participation question. Let me go ahead and stop the share here. Now, the very last thing I want to talk about quickly today is section 1.2. Honestly, 1.2 does not add a lot of new material to what we've already done for 1.1. It just adds some slightly new vocabulary when we're talking about matrices. So let me go ahead and talk about that real quick in the next 5-10 minutes, and then we'll call it a day. All right. So 1.2. 1.2 is all about, okay, so we know a system of linear equations can be represented as a matrix. That's all fine and good, but how do we know when a matrix has been reduced enough? We know we can use row operations to modify one row with another row, but how do we know we've done the row operations to find a solution? How do we know when we have it in a format where we can read a solution, where we can find the solution, right? So there are two formats for a matrix that tell us when we have arrived at a solution. The first form is called echelon form. So a matrix is in echelon form. Sometimes this is also called row echelon form. Sometimes it's called row echelon form in other textbooks. We call it row echelon form because we're using row reduction, or we're using row operations to get it into echelon form. So if you were to look at your calculator and you look at how to type a matrix in your calculator, you're going to see echelon form is abbreviated as REF. That stands for row echelon form. So what makes a matrix echelon form? Well, it happens if three things occur. One, all non-zero rows are above rows of all zeros. In other words, if you have a row which has all zeros, we want that row to be at the bottom, right? We want a row of all zeros to be towards the bottom, not at the top. Okay? 2, each leading non-zero entry, each leading non-zero entry of a row, which this has a special name. This is called a pivot position. A pivot position or a pivot entry is just where you have this non-zero entry, which is the first non-zero entry for a row, but we're going to require that it is in a column to the right of the leading entry for the above row. Now I know this is kind of worded kind of strangely. I'm going to show you an example of this in just a moment. In fact, when we were solving that matrix earlier and reducing that matrix, this was exactly the pattern we were having happen. And I'll highlight that in just a moment. And then thirdly, we want to require each pivot has all zeros below it, right? So think back to the example when we were trying to isolate x1. We wanted everything below x1 for that first equation to be zeroed out, so that was the only x1, right? That then made it a pivot. So if we look back at what did we do, well, that reduced matrix, we had simplified it to the form of, let's see, let me pull it up. What did we have? Right. We had 1, -2, 1, 0, 0, 2, -8, 8, 0, 0, 30, -30, right? So all non-zero rows are above rows of all zeros. Well, in this example, we don't have a row of all zeros, but if we did, we would want the row of all zeros to be at the bottom. So note, one thing you can always do with row operation is that if you wanted, you could just swap 2 rows if you like. That's okay. Why is that okay? Remember, each row represents an equation, right? So if you're listing out 3 equations as rows, swapping the order of rows just means you're swapping the order in which you've written your 3 equations. Does that change the problem, whether you write equation 1, equation 2, equation 3, versus if you write equation 1, equation 3, equation 2? No, it doesn't change the problem. It's still the same problem. So you can always swap rows. So if while you're row reducing a matrix, if you're doing these row operations, if you get a row of all zeros somewhere in the middle, you can always swap it with the bottom row and put it at the bottom. Okay, so number 1, check. Number 2, each leading non-zero entry of a row, this is called a pivot, is in a column to the right of a leading entry for the above row. So look at 2 here. This is the leading non-zero entry of row 2. It is in a column to the right of the leading entry in row 1, right? So in other words, we want this staircase pattern to happen. The same thing happens down here. Partly, I also want to highlight here, the requirement to be a pivot means in part 3 here, each pivot has all zeros below it, right? So if I instead, let's say I give you an example that looks like 1, 1, 1, 0, 1, 1, 0, 1, 1, 0, 0, 0, right? In this case, okay, here's a pivot. Now when I look at row 2, this one here is the first non-zero entry, but it does not have all zeros below it. So I wouldn't call this a pivot yet. In fact, if I wanted, okay, I could call this a pivot because it has zeros below it. But this one in the second row, I would not call a pivot because it has a non-zero entry below it, right? So not every row necessarily has a pivot. Part of the requirement to be a pivot is that step 3 also holds. To be a pivot, each pivot means you have zeros below it. Now, of course, we could continue to reduce this example. We could get rid of this 1, 1 in row 3, and then row 2 would have a pivot. But in its current form, we do not have a pivot there. Right? Okay. The point I'm getting at here is that when we were solving this earlier example, what we were really doing was row reducing the matrix, trying to force it to get into echelon form. As we continue the class, we're going to talk more about how do we do this, how do we do this in a smart way so we're not wasting our time, so on and so forth. General idea, the general approach, and we'll talk about this more tomorrow, is that you want to basically start with your first column, and you would like to try to get a pivot in the first column if possible. Well, if you can, you'd like it to be at the very top in the top left corner because you need this staircase pattern. The next pivot in the next column has to be below and to the right, right? So in order for that to happen, in order to have as many pivots as possible, you want your first pivot to start in the top left corner. That's going to be a general approach for this kind of problem. Again, we'll talk more about that tomorrow. I just want to introduce how to recognize a matrix in these different formats, okay? So this is called echelon form. But we can go one step further, and we can say a matrix is in reduced echelon form. And just like above, sometimes in some textbooks, they might call it row reduced echelon form, in which case they might abbreviate this as RREF. And in fact, in your calculator, if you have like a TI-83 or a TI-84, there are matrix operations that will turn a matrix into reduced echelon form, and that's the RREF command. We can talk about that more in office hours if you want to know how to do that. Right, okay. So what does it mean to be in reduced echelon form? Well, it means above holds, right? So 1, 2, 3 happens here. And we're also going to require each pivot is the number 1. How do you make that happen? Well, you could modify a row by dividing by something. Remember in that example I just erased here, that third row had 30, or was it negative 30? Let me look back. It was 30, negative 30. I could have taken row 3 and just divided it by 30, right? It doesn't change the problem, right? Because we already know x3 is negative 1. If you take row 3 and divide it by 30, you get 1, negative 1. Well, in that case, the pivot in the third row or the third column just became 1. So you can make that happen. And then additionally, we're going to require all, let me make sure I'm writing this correctly. each pivot has all zeros above the pivot. Now, we didn't do that when we were reducing our matrix earlier. However, if you go back and look at the textbook in section 1.1, at that example we were working through, when they continue reducing it in the textbook, they get all zeros above and below a pivot. Echelon form only requires you have all zeros below it, whereas reduced echelon form says we also want all zeros above the pivot. When you do that, then you end up with 1 at your pivot locations, zeros elsewhere. And in fact, if you go back and continue reducing that example we were looking at, you're going to get 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, negative 1. Now, what's nice about this reduced echelon form is that we can see what actually happened. When you have it in reduced echelon form, the answer to the system is right here. Right? Here are our 3 pivots. We have all zeros above and below. And then lo and behold, the equals column is telling us what each pivot, what each variable is equal to. So this is one way of when you have a matrix in reduced echelon form, it's telling you what the answer is. Now we're going to see as we continue, there are special cases that can happen here. What if you don't have a pivot for every column? What if you're missing pivots? Those are special cases that we're going to look at. Because this specific example, this meant we had only one solution. X1 had to be 1. X2 had to be 0. X3 had to be negative 1. We had no wiggle room. There were no other variables. There were no other numbers for X1, X2, X3 that would work. This was the only pair of variables that would solve this system. It had a single solution. So we're going to look more at okay, how can we tell when a matrix has infinitely many solutions? When does it have one solution? Or when does it have no solution? Which we've already seen today. No solution means you're going to have a leading non-zero entry in your equals column, right? As we saw with that other example earlier. Okay. There are other examples in 1.2 that talk more about how to tell the difference between echelon form and reduced echelon form. If you want to look at those examples, those are available to you. Yeah, I guess. Yeah, let me go ahead and cover some of this vocabulary before we wrap up for today. The last thing I want to highlight here, let me make sure. Yeah, okay, good. The last thing I want to highlight here is that, so we saw, let me rewrite this. We saw with this example that we had a pivot for each column. In other words, we had a pivot for each variable. So a variable with no pivot in its column is called a free variable. What does it mean to be a free variable? Well, that just means that for that particular column, for that particular variable, it's not locked in. We don't have a row that says x3 has to equal something, right? If I modify this matrix, if I put zeros here, now x3 is a free variable. But also note, this is still consistent because I don't have a non-zero in this entry, right? I don't have a non-zero leading entry, right? In other words, I don't have a pivot in the equals column. A matrix is inconsistent if you have a pivot in the equals column. But if there is no pivot in the equals column, it is consistent. So this matrix still has a solution, but what does this mean? Well, we have no equation that says what x3 equals. What does that tell us about x3? It tells us x3 can be anything. We'll see examples of that later. What does that mean? What does that look like? The point here is that when you have a free variable and it's still consistent, this is the situation when you're going to have infinitely many solutions. So we'll talk more about this tomorrow. But the real point I want to drive home here is that even this form, while I have a free variable, this is still reduced echelon form, right? I have all non-zero rows are above rows of all zeros. My row of all zeros is at the bottom. Each leading non-zero entry of a row, a pivot, is in a column to the right of the leading entry for the above row. Each pivot has all zeros below. Each pivot is a 1. So I'm always going to box pivots like this because pivots are going to be super key for the rest of this class. I'm going to put boxes around them to highlight their pivots. And 5, each pivot has all zeros above the pivot as well. So we see that here, right? So great. I'm going to leave that here. If you have other questions, please feel free to email me, or you can come to my office hours. We're going to start the office hours next week. And homework 1 will be published to Canvas later today, so that will be made available. Otherwise, have a great day, guys. Best of luck, and by all means, please do reach out to me if you're in trouble. All right, that's all for today.